So hi guys, we are back with another video that is we're going to discuss the structured essay of the paper 11. So right, uh, so yeah, it's the paper 11. So this paper 11 is like the 2019 past paper. This is the 2019 past paper, right? So we're going to discuss the structured essay of it. So here in this structured essay, of course, what we have chosen is like one question from heat and another question from waves and oscillation, the optics part. So the question from the heat is going to be the Searle's apparatus problem, and then the experiment that we will encounter in the optics part would be the spectrometer. So yeah, let's get started with. All right, so it says an incomplete diagram of an experimental setup to determine the thermal conductivity of a metal, right, by the Searle's method is shown below. Okay, so let us see what the first problem is. What are the purposes of inserting tubes P and Q into the steam generator? Okay, so first of all, why do we use a steam generator? Actually, we heat this metal rod by using steam. All right, so to generate the steam that is required to heat this metal rod, we need a steam generator. So inside this steam generator, there's two tubes P and Q. So the tube P is actually used in order to supply the generated steam. Actually, the steam that is generated inside the steam generator will move across this P tube, right? So therefore, that is used to supply the generated steam. Okay. So yeah, so therefore the steam generator P is used in order to supply the generated steam. Okay, so what is the purpose of the tube Q? What do you think? What might be the purpose of the tube Q? Actually, assume that there's no tube Q. There's no tube Q. What happens is when you heat the when you supply heat to the steam generator continuously, it will continuously produce steam inside the generator. So when, like, what happens when the steam generation occurs is the pressure inside the steam generator would reach to a dangerous level, right? So therefore, like, in order to prevent the pressure from reaching to a dangerous level, what they have done is they have made a hole, and then like they have exposed to this steam generator to the outer atmosphere. In that case, when the steam generates to a higher level, the liquid from the water or the liquid will rise up, which means that the uh, the pressure level will decrease, which means you can maintain the pressure inside the uh, steam generator at a required level, right? So that is the purpose, simply in order to prevent the pressure from reaching an unfavorable level. All right guys, let's get moving on to the B part. So here what it says is proper connections of steam and water supply to Searle's apparatus are necessary to obtain accurate results. Accordingly, select each connection and give reasons. Like what they are simply saying is like select the proper connections to steam and water, right? And give the reasons, right, to steam supply. So from where are we going to supply steam? That's what we need to consider. We can either supply steam from the A inlet, that we can consider A as the inlet and B as the outlet, or else the other way around is also possible. Like we can consider B as the inlet and A as the outlet. But out of these two, what are we going to decide? That is the question here. Actually, the answer should be we need to select A as the inlet and B as the outlet. What they are asking is the steam supply. We need to supply steam from where? A, right? So they have asked the reasons as well. So if you see, guys, like there's plenty of reasons, right? So the reasons, the main key factor for all these reasons are mostly the density of steam, right? The density of steam is less than the density of air. So if the density of steam is less than the density of air, when you send it from the top, what happens is it will completely fill up the, first of all, it will fill the top chamber, right? Because like it always prefers to exist on the top of air since it has a lesser density. So this is air, right? So this is air maybe, right? So it always prefers to stay on the top. Once this space is completely occupied, it has no other options, so it will slightly go below, right? Likewise, it will completely fill up the steam chamber, right? Actually this is the desired outcome, guys, right? So this is the desired outcome, because like what we need to do is, like what we actually desire is to completely fill the steam chamber with steam. So then only we can say exactly that this is in the temperature, this is in contact with steam, it seems. Then only we can say it, right? So therefore this is actually the desired reason. So since this is the desired reason, we need to pass steam from the A inlet and we need to get it out from the B outlet, right? So now that is the main reason. So you can answer it either in a positive way or else a negative way as well, right? Like when you consider reviews, right, like discussions, past paper discussions, it's not only the reason or the answer that you need to focus on. Like if you need the answer, of course you can go through a past paper answer and then like figure it out, right? But actually that is not what's required. Like you need to understand answer is not what matters when you go through these kind of discussion videos. What matters is actually the reasons and then the approach, right? So simply like you can answer this problem with a positive approach as well. Like okay, you can say if you pass it through A, since the density of steam is less than air, it will completely fill up the steam chamber. You can answer it in a negative way as well, right? Like it's like this. So you can say if you pass steam from the below, what will happen is, since the density of steam is less than the density of air, it will straight away move on across the steam outlet. Always it prefers to stay on the top of air, right? So therefore straight away it moves upwards. So it's not going to in that case fill the steam chamber. In that case we can't say that the steam is in contact with this portion of the rod. All right, so in that way also you can answer. And then I'll give you one more reason, right? So usually it doesn't matter whether you pass steam from the top entrance or the bottom entrance, whatever it is, after a certain amount of steam is filled in the chamber, what's going to happen is the steam is going to condense into water. It's going to condense into water, and definitely it's going to partially block the entrance B as well. It's going to block the entrance B as well. So it's actually like this condensation and blocking of the entrance B will not make a big effect if you send the steam from the top, because completely it will fill the steam chamber and then only reach this point, right? So but now assume you are supplying steam from the below. Now if the steam entrance is blocked, now it's an issue actually. Like you can't pass steam, the desired amount of steam, to the steam chamber, right? So that is also not going to be a good thing, right? So that's a negative impact as well. So like remember that is also a good reason, right? So hopefully like all these reasons that I mentioned are going to be fine. So I'll mention them as well, right? right? So condensed, simply since the density of steam is less than the air, it will completely occupy the space in the steam chamber, right? Therefore only you need to send it from A, or else like the condensed steam might block the B entrance, right? So if it blocks the B entrance, like it will be difficult for us to send steam through B. Like, you need to write complete answers, right? So like I have given you the idea. Right, let us move on to the next thing, that is water supply, right? Simply, now we need to see from which entrance do we need to supply water. Either we can supply it through M and get it out from L, or else we can supply it through M and get it out from M, right? So you need to decide which is the most suitable. Now for us to understand this, guys, like, so you need to know that this is in mostly in 100 degrees Celsius around, right? So now when you move towards the right, the temperature is going to decrease. That is pretty obvious, right? So when you move towards the right, the temperature is going step by step decrease. So if we assume the temperature here is theta 1, if we assume the temperature here is theta uh, theta dash and theta double dash. So obviously you know theta dash is greater than theta double dash. So somehow water should be absorbing heat, right? So cold water, if we send the cold water from this side, it goes, right? It goes, and when it goes over this, right? When it goes over this, since it is going from a lower temperature region, lower temperature region to a higher temperature region, always the water is going to absorb heat. Since it's going from a lower temperature region to a higher temperature region, to like, actually the right side is a lower temperature region and left side is a higher temperature region. So when it's going through this route M to L, is going from a lower temperature region to a higher temperature region. In that case, it can completely absorb, it can only absorb heat energy, right? So that is one reason. Actually, therefore, so we need to send it through M, right? If we send it through M, it's going to be very suitable, because like in that case, we can confirm that water will absorb the maximum amount of heat. That's one reason. And then also, like, if you send it through M to L only, you will be able to observe a considerable temperature change, temperature difference, because initially water is going to be cold. If it goes from lower temperature to higher temperature, it will be able to absorb heat. In that case, in this case, of course, the temperature will rise. Then only you will be able to attain a considerable amount of temperature difference, right? That is T3 minus T4. This will be considerable amount only if you send it from this route, right? So like that is another reason. And then also, like, if only if you send the water from M to L, you can confirm that it will reach a steady state quickly, right? A steady temperature quickly, right? So those are the reasons. Like, you can mention one out of the three reasons that I mentioned. The three reasons that I mentioned were positive reasons. So like it's like this, right? So if you send if you pass water, if you pass temperature from uh, if you pass water from L to M, it's like you can mention all the negative impacts, right? So higher temperature to lower temperature, so the amount of heat absorbed will be less. So likewise stuff, you can comment on the negative impacts as well, but I guess the positive impact is going to be fine, right? So M to L. So therefore I guess the reason these would be the reasons, guys. Like water will absorb maximum amount of heat only if it is sent through M and M to L, and also a considerable temperature difference between theta 3 and theta 4 can be obtained when it is sent through M to L. And also, when the water is sent through M to L, it would reach a steady temperature somewhat faster, right? So these would be the reasons. You have to mention it on your own words, however is very clear, right? All right, fine. Okay, let's get started with the next problem. So in the C part, what they are saying is for us to state three more measuring instruments needed in this experiment and briefly state the specific measurement taken by each of them. What do we need further? Like actually guys, we need a to be honest, like to find the conductivity of this metal, we need the area, right? Isn't it? We need the area. Actually, we need the cross-sectional area. We need the cross-sectional area of this. We need the cross-sectional area of this rod, and we need the cross-sectional area. So how would we find the cross-sectional area of this rod? In order to find the cross-sectional area, so cross-sectional area is pi r squared. Pi r squared, right? It's a rod, right? Pi r squared means like r means the diameter divided by 2. Pi this pi r squared. So to find the diameter of the rod, what do we need? We need a vernier caliper, right? We can use a vernier caliper. What is the measurement? The cross-sectional area of the rod. All right, cross-sectional area of the rod. So what is the other another equipment that we might need? So like, okay, we also need to measure the distance between these two thermometers, right? Isn't it? We need to actually measure the distance between the distance between these two, d. We need to measure d. To measure the distance between these two thermometers, we can either use vernier caliper or else a meter ruler is also possible, right? Meter ruler. Distance between T1 and T2. What else? Also, we need to find the flow rate, right? We need to find the mass flow rate, isn't it? We need to find the mass flow rate of water, right? So actually, therefore, like mass flow rate means what? Mass flow rate means m dot means the amount of water collected, right? The amount of water collected, the mass of the water collected divided by the time taken, right? So how do you measure the time? To measure the time, of course, you need a stopwatch, right? You need to have a stopwatch to measure the mass. Of course, mass of the water collected, you need to have a balance, right? So you can't simply write it as balance, guys. Like make sure to mention a balance which is used in your school laboratories, right? So in your school laboratories, you might have electronic balancers, triple beam balancers, chemical balancers, right? So out of these three, you can mention either one of it, right? So therefore, like we can mention a stopwatch. The reason is what? To measure the time of water collected. All right, and a balance, right? Maybe I'll write it as triple beam balance, right? Triple beam balance. This is the fourth one, right? Like I'm gonna give you an extra to measure what? To measure the mass of water collected. All right, okay, fine, that's cool. Right, so let us move on to the next. All right, so if you see the D, it says the separation between the thermometers theta 1 and theta 2 is 8 centimeters, which is what they have found is this right, the distance between T1 and T2. So the distance between T1 and T2 is 8 centimeters. If the constant temperature readings of theta 1 and theta 2 are this and this, calculate the temperature gradient. Actually, guys, like to find the temperature gradient, it's quite simple, right? So temperature gradient is what? Simply theta 1 minus theta 2, temperature difference delta T over delta D. Actually, temperature difference is delta T over delta D, the gradient, right? If it is a rate, of course, below you need to write the time taken. But since it is a gradient, obviously you need to understand that it is the temperature difference divided by the distance between those two differences, right? So they have given T1 to be at 73.8 and 59.2. These are pretty simple calculation problems, right? Like if you can't get these answers, of course, then there's no point. Delta T is, you need to represent it in meters. All right. So if you do that, of course, you are going to get something around 182.5 degrees Celsius per meter. This is the temperature gradient. All right. This is the temperature gradient. I think we do not have to analyze further about that because it's a pretty simple question. Okay, so this is kind of a good question though. So the E part, what they're saying in this is, does this temperature gradient vary along the road? Now, okay, so we have found that the temperature gradient is 182.5. Like will it be varying around the rod, like along the rod? So if you see the rod, when we move from the left to right along the rod, one thing that we could see is it's completely insulated, right? It's well lagged, isn't it? It's well lagged. If it is well lagged, what is it? The thing is, if it is well lagged, then of course there is no heat loss from the rod to the environment. No heat loss, right? No heat loss. If there is no heat loss, the temperature should only be it will be only be conducted from left to right. There's no heat loss. Therefore, the temperature gradient will not change. No. The reason is briefly explained, right? When they say briefly explain, don't go to write passages and all. It's like they're not going to read some, like if your papers are analyzed by maybe a very lazy supervisor, I'm not saying everyone is the same. I'm just saying, right? So like if someone analyzes it, so maybe if you kind of okay, let it be like you know the answer. But if you kind of write it in paragraphs and all, most of the time they might lose you. I mean, they might lose the answer. I mean, they might not exactly see where the answer is, right? The exact key point that they are searching for. They might not be able to find it. So make sure to write when you're writing a structured question, guys. Make sure to write the answer to the key point, right? To the pinpoint, you need to write the answer. Do not go to write explain. Like when they say briefly explain, briefly explain. Simply you say since there is no heat loss. No heat loss. You do not have to write further. Since there is no heat loss, the temperature gradient will not vary. That is perfectly enough, right? If there is heat loss only, the temperature gradient would vary. If not, of course, it's going to be constant throughout. All right. So hope you understood. At the thermal steady state, they're saying the next thing. At the thermal steady state, the difference in temperature are theta 3 and T3 and T4 are 9.5 centimeter, 9.5 degrees Celsius, right? So at the thermal steady state, when the temperatures reach to a steady state, which means if once they reach to a situation where it doesn't vary anymore, it's like it doesn't fluctuate anymore, simply, right? So they have given temperature, the difference between these two thermometer readings is 9.5, it seems, right? So okay, fine. And then the flow rate means simply, the flow rate means m dot, which is like m over t, right? That is what flow rate is 120 grams per minute, right? Okay, so calculate the rate of heat absorption. So you need to understand, guys, like what they ask is not heat absorption, the rate of heat absorption. When they ask the rate of heat absorption, it is Q over T. Heat absorbed is Q. Actually, what is the water going to do? The water column, when you send it through M, it's going to absorb heat from the rod. It's going to absorb heat from the rod. Let us assume the heat absorbed from the rod is Q, and the rate of heat absorbed is Q over time, right? So that is equal to, actually, so you can write it as this. So what is the heat absorbed? Heat absorbed is mc delta theta, right? So the rate of heat absorbed means divide both sides by E, right? So this is the rate of heat absorbed. MOT is the mass flow rate, that is m dot C delta T. What is m dot now? 120. You need to convert it into grams. Okay, kilograms per minute. You need to convert it into seconds. 4200, right? And the temperature difference is 9.5. So if you simplify this, you're gonna get an answer. So guys, it's going to be something around 79.8 watts. Right? 79.8 watts. Okay, so we have found the rate of heat absorbed by water, right? So now next, let us go for the next problem. If the cross-sectional area of the rod is this much, 12 square centimeters, calculate the thermal conductivity of the metal. Calculate the thermal conductivity of metal. State answer with SI units. So it is like this. So simply, you know the equation for the thermal conductivity, right? So the rate of heat absorbed by water should be equal to the rate, the heat conducted across the rod, right? Across the rod. So heat absorbed by the rate of heat absorbed is equal to this value. All right, Ka theta minus. So this is the temperature gradient. This is the temperature gradient. We already know this, right? Know this value. What we need to find is this. We already know this as well. They have given this as well. So Q over T is what? 79.8. What is K? That is what you need to find. Area is given to be as 12. You need to represent it in meter, square meter. So 10 to the power minus 4. So what is this? 182. The temperature gradient is 182.5. We have already found it. 182.5. All right. So if you subject K, you're going to get a value very closer to 364.4 watts per meters per Kelvin. You need to be very careful of the SI unit, right? So if you are not quite sure of the SI unit, just write, okay, this is what? This is square meters. This is what? This is degrees per square meters. Right? This is degrees per square meters, right? So like, just do the simplification and see. You will get this could be in degrees. Okay, SI units, right? So since they are asking it in SI units, rather than representing it in per degree Celsius, you can right? So the SI unit of temperature is Kelvin. So per Kelvin, right? So you can represent the temperature gradient in per Kelvin per meter. Kelvin per meter. Kelvin per meter and degree Celsius per meter is the same. Magnitude is going to be the same, right? Magnitude is going to be the same, only the value change, right? So guys, they are asking next, is it possible to use the Searle's method to find thermal conductivity of a poor conductor? Like, can we use thermal conductivity, the Searle's apparatus, to find the thermal conductivity of poor conductors? Actually, the answer would be no. So what might be the reason for this? The reason is, in a poor conductor, the temperature gradient, this temperature gradient, right? This temperature gradient would be a very small value, right? gradient would be a very small value. Like actually we will not be able to get a very large temperature gradient. I mean, like it will be a very small value, right? If it is a quite small value, actually the we won't be able to proceed with the experiment. The error percentage and all these stuff are going to be quite high. All right. So actually the temperature will not decrease much. I mean, like the temperature, right? So there'll not be a very considerable amount of temperature gradient. So that is the reason, right? So due to negligible temperature gradient, right? Temperature gradient in the poor conductor, right? So if the temperature gradient is quite negligible, then of course the rest of the stuff, the finding the K value, if this is very small and if it's negligible, we will not be able to find the K value accurately, right? So it's going to have a very high error percentage. So that's not suitable, right? So that's the reason. So guys, like we have discussed the Searle's apparatus, right? So Searle's apparatus for you guys in the 2019 paper. So I guess you might have got a very clear idea on what it is. So let us move on to the next experiment, that is going to be the spirometer. All right.